Welcome to class. Let's do it. So to start, which solution has the higher pH, a 0.001 molar solution of sodium hydroxide or a 0.001 molar solution of barium hydroxide? So think about it, make your choice. Okay, and also think about why. So when I think about these problems, first of all, we need to get good at this. Are these strong bases or weak bases? Hopefully you said, hey, I know from that video we watched just the other day, sodium hydroxide and potassium hydroxide are strong bases. And we know that those heavier alkali earth metals like barium, calcium, strontium are also strong bases. So we have these two compounds, okay? They both fully ionize in water. And when they ionize, they produce these ions, Na plus and hydroxide ion, okay? And in this case, we have barium 2 plus and also hydroxide ions. But how many hydroxide ions do we have? Two, right? Okay. So when we think about which solution has the higher pH, let's just ignore that. Let's just think about, hey, which one has more hydroxide ion? Well, I would say, hey, definitely more hydroxide happening here with the barium hydroxide. So if something has more hydroxide, let's think about pH. Low pH is acidic. These are more basic, so the higher pH is going to be the barium hydroxide. Okay, I hope that is okay for you. So what are we talking about? This is your only assignment for Thursday or Friday. Let me know if you have questions in the ed puzzle, and I'll look at them and get back to you. Okay, so let's just talk about weak acids. So weak acids are great versus strong bases and strong acids. They don't fully ionize in solution. Sorry, they don't fully ionize in solution. So um, luckily, we're pretty good at equilibrium these days. So here's what I want you to do first. I want you to write out the equilibrium constant expression for our delightful situation here. Oops, sorry. For our, there we go. Can I move this? There we go. For our generic acid. So write it out here. Take a second. Okay, so here's what I got. I got that K is equal to our products, right? It's always the products first. I like to write the acid first, the H plus ion, then the anion, I don't know, over concentration of HA. I hope you got that too. Now, what's special about this is not just any old K. This is called Ka. It's called the acid dissociation constant. Okay, so this special Ka, and this works for any acid. Okay, so you're going to see where it casts off that proton. Hope you did well on that. What does the magnitude of Ka mean? So take a second. Let's think about this. What does a large K mean for the strength of an acid? Okay, so big K, right? Big K means we have a lot of product, right? Which are those ions. And the more you ionize, the more strength you have as an acid, right? So a big K is going to say that you have, sorry, I'll move this, that you are better at ionizing, which means you are stronger. Okay, hope that's working out for people. So let's start doing some problems. Whew, okay, this one's going to get interesting. I need to write some things on paper so that I can get rid of this. So remember, when we think about weak acids, they're always part of an equilibrium system. So here's a problem we're being given. We have been told, okay, we're looking at something called formic acid, HCOOH. First thing you're always going to want to do is just get the equation for how it ionizes written out. So we know it's weak, okay? It's not one of our 7 strong acids that we talked about yesterday, which means we know it produces H plus ions and these COOH anions, okay? So we're pretty good to go there. So we know that. So then what else we should do? Well, the first step, and we're going to pause the video, we should write the equilibrium expression for formic acid. So take a second, write the equilibrium expression for this. Hopefully you did this. I got Ka equals H plus over COOH with COOH minus over HCOOH. Okay, so there's my expression. What other information do we have? Well, We were told that we have a 0.10 molar solution of HCOOH. Okay. We're also told that pH equals 2.38. So let's talk about some of this information, okay? And what are we solving for? We are solving for Ka. So let's put a circle around this. I'm going to make this big. So, okay. So here's our problem. So we are trying to solve for Ka. Let's just think about what we know. We know pH, okay? pH is just equal to the negative log of hydrogen ion concentration. Okay, so that's pretty nice. If we know pH, we can get hydrogen ion concentration at equilibrium. So that's good. What's the relationship between hydrogen ion concentration and this anion concentration? Right, yeah, it's 1 to 1. So we know this too. Now, quick question. Using Ka, where do we need to get these values from? Should they be initial values or should they be equilibrium values? I hope you said equilibrium. And this right here, this is an initial value. So we don't quite have the equilibrium value, which means we're going to need to use an ICE table. Okay, so to use an ICE table, you label it at the top with the species that are ionizing. Okay, and it's just a way to help you visually figure out what's going on. So initially, let's do this in orange. Initially, we had 0.10 molar of our acid. We had no hydrogen ion, no anion. Okay, we're just going to represent these as x. Okay, so this is plus x, this is plus x, this is minus x. Okay, now, do we know what x is going to be? Can we figure any of this out? And I say we can. Let's do this pH calculation over here. So we need to take the pH of 2.38. It's equal to the negative log of our hydrogen ion concentration. Can you solve for the hydrogen ion concentration? Make it happen. Okay, so here's what we get. We get negative 2.38 is equal to the log of the hydrogen ion concentration. Okay. 10 to the negative 2.38 is equal to the hydrogen ion concentration. Okay, 10 to the negative 2.38 is, did you get it? 4.2 times 10 to the negative third molar. Okay, so remember, this is hydrogen ion concentration, which is this right here in our table. So now we know that the equilibrium concentration of hydrogen ion is this, which is also the concentration of our anion, okay, which we now know is X. So the equilibrium amount of our acid is 0.10 minus 4.2 times 10 to the negative third. Cool. Okay, so now we have our equilibrium amounts. So we can check this off. Okay, now we're going to plug all of these in. So let's do it in blue down here. So we have 4.2 times 10 to the minus 3. Is it okay if I just square it so I don't have to write the whole thing out? We get why it's squared. I plugged in this for this and this for that. Okay, we're going to put it all over E, the equilibrium amount of our acid. Now something is kind of interesting here, something that we're going to see in the future. We have this number. Think about 0.10 with subtract 4.2 times 10 to the negative third. Now, this is outside of the significance of this number. So we can actually ignore this because it's too small to make a difference. And now you're like, Miss Brown, I could do that math. That's not a big deal. But in the future, this is going to be an x, and it's going to be in a place that is going to force us to do the quadratic equation. And if we can avoid doing the quadratic equation, we want to, right? Okay, so what we're going to do is 0.10 is going to go down here because we get to ignore the rest of that, okay? This is going to equal Ka. So can you solve for Ka? I hope so. I got 1.8 times 10 to the negative fourth. No units, right? Anytime we do a K. Good. Okay. I hope that went all right for you. Can I get out of the video? I don't know. Uh-oh. I lost everything. My whole screen is blank. There we go. I think I can make it smaller. Boom. There we go. I'm out of my presentation now. So here are just some steps, kind of like what we did. Hopefully this is still shooting. It is. Always write the equilibrium. Show the ionization of that. Write your equilibrium expression. Okay. Express everything that you can. Write out your information and solve for things if you need to for X. Okay. let's do a couple more problems. Let's see if this will work. Okay, let's keep presenting. Okay, so we have a new problem. Very exciting. So let's try our new problem. And I'll help you through most of this, but maybe a little bit less of it. And we'll just see how it goes. Okay, so we are going to talk about acetic acid. Now, you probably don't have your acids memorized, and that's okay. So I will tell you what acetic acid is. Acetic acid is, first of all, the thing that makes vinegar acidic. Acetic acid is based on the acetate ion, C2H3O2 minus. So you pop a proton on there, that's acetic acid. It is not one of our 7 strong acids. So it's in equilibrium with its ions. And we know there's only one hydrogen out here, so we're going to pop off a proton and leave the rest of the ion behind. Okay, so there's that. Now, ooh, they're giving us Ka. This is going to be an interesting problem. Let's just write our acid dissociation constant expression here. Okay, so give it a sec, write it out. Okay, here's what I got. Okay, so there we go. Okay, pretty good. So now let's just think about what we're solving for and what we're trying to figure out. We know Ka. All right, we have some information. Ka is equal to 1.8 times 10 to the negative fifth. Okay, we're trying to solve for pH. What's the thing that gets us pH? The one thing we need? Well, it's hydrogen ion concentration, right? So we need to somehow get from Ka to hydrogen ion concentration and then to pH. Probably the only way we're going to be able to do this is using an ice table. Okay, so I'll put my ice table up here. Okay, we have our HC2H3O2, H plus, C2H3O2. So same situation. We're going to start out with 0.30 molar of our acetic acid, no hydrogen ion, no acetate ion. Okay, plus X, minus X. Okay, so now this is kind of interesting. Instead of having numbers out here, we're going to end up having everything in terms of X, which is going to work because as long as we just have one variable, we can solve for it. So here we go. We get 0.30. Sorry, I kind of got out of control there. 0.30 minus X, X, and X. So let's plug these values back in up here. So Ka, let's use orange now. Ka is 1.8 times 10 to the negative fifth, which is going to be equal to our hydrogen ion concentration, which is right here, okay? X, acetate ion concentration, also X, so that's going to be X squared on the top, divided by 0.30 minus X. Now, if we have X in the denominator, we are going to have to use the quadratic equation to solve for X. That sounds super annoying. So how do we know when we can ignore X? Well, when things are more than 3 powers of 10 away, so this is 10 to the minus 1, this is 10 to the minus 5, when they are more than, so 10 to the minus 4 away from each other, they are 4 powers of 10 away, so this is farther out than to make a difference down here. So we can effectively ignore this minus X, and now we can just solve for X squared. Seems pretty straightforward, right? So solve for X squared, get me a number. Okay, and you should have gotten that X squared was 5.4 times 10 to the negative 6. And then when we solve for X, 2.3 times 10 to the negative third equals X. Okay, now what is X again? Yeah, X is our hydrogen ion concentration. So to get the pH, right, pH equals the negative log of our hydrogen ion concentration. And make sure you're using parentheses in your calculator. Make sure you can get the right number. So take the negative log of 2.3 times 10 to the negative third, and I got it to be 2.64. Okay. Let's try another one. Maybe you can do a little bit more on your own. Okay. Step 1. HCN. What ions does it produce? Hopefully you got that. Okay. And so Ka, its equilibrium constant expression, okay, looking good. Now we know Ka, again, we're solving for pH. So we're gonna need to go from Ka to our hydrogen ion concentration to our pH. Okay, we can do that. This is just like what we did before, right? Just like what we did before, not too shabby. Okay, let's work on that ice table. What I want you to do, I want you to work through the video right now, and I want you to tell me what you got for the value of the equilibrium amount of HCN. Okay, we'll just start filling this out. Okay, so let's see how you did. Hopefully you got this here, plus x, minus x. Hopefully you got 0.20 minus x. If you already said you wanted to ignore the x, that's great too. Okay, so I don't know why I'm writing pluses, but those values are x and x. So very similar thing going on here when we plug this all back in, right? We know that our Ka is 4.9 times 10 to the negative 10. Now, is that really small? Yeah, that's really small. That's way more than 3 powers of 10 away from this 0.20 number, right? So we can ignore x, okay? So we're going to be equal to, let's plug our x's back in, x squared over 0.20. Nice. Okay, so solve for x. So you should have gotten that x equals 9.9 times 10 to the negative 6. Now solve for the pH. Good. Okay, we're getting better. We're already getting better. Okay. Okay, so this problem is going to ask about ionization, and let's not worry about that yet. Let's do this beast of a problem, okay? So this is a time where we are going to use the quadratic equation. Oofda. Okay, so here we go. We're talking HF. So first thing first, HF is a weak acid. We're going to have hydrogen ions and fluoride ions in solution, Ka. That all looks pretty good to me, okay? And so let's just get that ice table set up. I'll do it in green this time. HF, H plus. So we're talking 0.10 here. We're talking 0 and 0 here, okay? Plus x, minus x. So this is 0.10 minus x. This is x, and this is x. So when we go to plug everything back in, okay, Ka is 6.8 times 10 to the negative 4. And that's going to be equal to hydrogen ion concentration, which is x, multiplied by fluoride concentration, which is also x, all over 0.10. Now, can we ignore the x? So this is 10 to the negative 1. This is 10 to the negative 4. That's 3 powers of 10 away. We can't ignore it. It's too much of a difference. It affects it. So we need to write minus x in here. Whew. Okay, this is annoying. So now we got to use that quadratic equation. So first things first, we need to rearrange this. Okay, so what we end up getting is, let's multiply this over, right? So we'll get so let's distribute. We'll get 6.8 times 10 to the negative 5th from multiplying these two together, minus 6.8 times 10 to the negative 4th x, okay? And that's going to equal x squared. And then let's just get everything over on the side of x squared. Keep x squared positive so that a is 1. Okay, so we're going to get 0 is equal to x squared plus 6.8 times 10 to the negative 4th x minus 6.8 times 10 to the negative 5th. Okay, so let's not forget, this is A, this is B, and this is C. Okay, so what is it? It's B plus or minus the square root of B squared minus 4AC all over 2, right? I think so. I think that's right. Right, let's double check. Oh, opposite of B. Right. Yep, opposite of B. You're like, you guys all have the song. You're yelling at me at home. But I think I did that right. Okay. So we have this all set up. So we just need to plug these things in, right? So opposite of B is going to be negative 6.8. Draw a line here. Negative 6. So here's B. Opposite of B, 6.8 times 10 to the negative 4. Plus or minus the square root of B squared times 10 to the negative 4th times. So that's all minus 4. A is 1, so we just need to multiply by C. 6.8 times 10 to the negative 5th. Oh, I'm running out of room. Okay, all over. Oh, it's supposed to be 2A, right? 2A, but A is 1, so it's just 2. Okay, so there we go. So now you just need to solve this bad boy. Now, you're going to get plus and minus. So what happens if you get a negative number? You're just going to ignore it, right? Because we're solving for X, and X is the concentration of hydrogen ion, and we can't have a negative concentration of hydrogen ion. It does not exist in the natural world, okay? So there we go. Get me a number. So X is going to be equal to 7.9 times 10 to the minus third. Can you get the pH from this hydrogen ion concentration? Okay, good. pH should be 2.10. Whew, lots of problems. Nice job at home. Let's just talk really quickly about something called percent ionization. So all percent ionization is, it's just another way that we can think about this. We measure acid strength. So what you do, you take the number of ions coming from HA, right? Usually we just call it, hey, it's H plus. You just use the hydrogen ion concentration. You put that over the concentration of original HA, right? Initial, and you multiply that by 100% because this would be a decimal, so we multiply by 100%. So let's just do this problem real quick. If a solution of 0.035 molar HNO2 nitrous acid, so 0.035, okay, divided by, sorry, in the denominator, 3.7 times 10 to the negative third on top, okay? And let me move my camera out of the way. Okay, so it will contain 3.7 times 10 to the negative third molar hydrogen ion. What is its percent ionization? So just get a number for me. And hopefully you got 11%. Okay, so that's percent ionization. Not a huge deal. And that's where we left off in class. That was a lot, so let me know if you have any questions, but those are those types of problems. We will also be practicing them on Monday. So don't worry, you will get more practice with all of this. Nice job. Thanks, everybody.